just kind of remind you what we did last time. We looked at how things dissolve in other things, and the takeaway here is in 151 or in intro chem, whatever you took, you guys probably learned like dissolves like, polar things dissolve polar things, non-polar things dissolve non-polar things. And here we have a little bit more nuanced explanation, and that is that things with similar intermolecular forces, they don't have to be the same, but they have to be similar energies, will interact with other molecules that have similar energies, that IMFs that hold them together. And the reason for that is, water likes being around other water molecules. If you're going to mix with that, the new interactions you make with water have to be as good, or maybe not quite as good, but they have to be close in energy to the energy you get from two water molecules interacting, right? These attractions lower the energy of your substance. And so if you're going to dissolve something in water, it has to keep that relatively low energy state. You can't put something that is going to have terrible interactions with water. It's not going to dissolve in water. And the same goes for nonpolar things. Two nonpolar things have very weak interactions with each other, with themselves, so they'll mix fine with each other. You're not like, so if you have, I'm not going to draw it out, but if you've got octane, C8H18, this stuff is nonpolar. It's long chain hydrocarbon. It does London dispersion forces, so they're very weak interactions, but they are strong enough to be liquid. This will dissolve with, this will mix with pentane, a shorter chain hydrocarbon. And the reason it mixes well is because they both have similar interactions with each other, and so they'll have with themselves. So they'll have similar interactions with each other, and they will mix just fine. But water will not mix with this because water likes itself too much. It's not going to want to break the connections between two water molecules to put this in the middle of it. All right, so that's why like dissolves like. You need to have relatively similar IMFs for things to dissolve within each other. So which of the following substances are insoluble in water? And I didn't start my thing yet, but hold on a second. I am inadequately prepared today, sorry. Come on, slow. There we go. Come on, clicker. There we go. Okay, so which of the following substances are insoluble in water? So one of those pretty obviously soluble, hopefully. The other two, you have to understand what kind of compounds they are. So the way you should think is water has strong IMFs, hydrogen bonding. That's what water does with other water molecules. So if you're going to dissolve in water, you need to have likewise very strong IMFs holding your particles together. Not too strong, but not too weak. So an ionic compound like NaCl, that is, ionic bonds are holding the cation and anion together. It's pretty strong, so that's probably going to dissolve in water. We know that. So let's see what people say. Oh, this keeps turning off now. We got it all over the place. That's good. So water probably will dissolve NaCl. We know that it does. If the charges were too high, like Mg and O, magnesium oxide, +2 and -2, maybe the ionic bond would be too strong for water to dissolve. And magnesium oxide is actually insoluble in water. Pentane, these are all, this is just an alkane, just a non-polar, 5 carbons with 10 hydrogens, that's it. That's going to have only London dispersion forces holding it together. They're very weak. And so that shouldn't dissolve in water because the interactions are too weak to compare with water's interactions. 2-pentanol is an alcohol, an OH group, and that OH group does hydrogen bonding. Very similar to what water does. And so we expect that will dissolve in water. So 2 of these are going to dissolve in water. And this keeps dying again. So pentane and, which one is insoluble? So pentane is immiscible. All right. By the way, immiscible, that's just another word for insoluble. They don't mix together. So the interactions between water are too strong. The interactions for water and pentane are too weak. And so they're just going to stay separate. They don't want to mix. Here's a nice close-up of what happens with the DNA base pairs. So you've got your DNA double helix. So there's the double helix part. And the base pairs, cytosine, guanine, adenine, thymine. These are the base pairs that interact with each other. This is an RNA strand coming in, I guess, and I don't know the term in biology. What is it? Transcription, that's what it is. So how do the base pairs hold the 2 helices together? Well, there you go, adenine and thymine. It's hydrogen bonding. That's it. There's no formal bond between these 2 base pairs. They're just holding each other together with these strong hydrogen bonds. Yeah?
I think it's making a new DNA strand, looks like in that photo.
I guess it would be a new strand because what RNA has uracil in it, not whatever. I am not strong in the whole DNA replication thing. I don't know the details, but these 2 helices these 2 strands have to be able to unzip for transcription to happen, and they unzip very easily because these are not a formal bond between the 2 base pairs. And in addition, these are why these 2 base pairs go together. Adenine and thymine, they interact perfectly because you have these 2 shapes that fit together perfectly. Guanine and cytosine have these 3 spots that fit together perfectly. And you can't mix cytosine with a cytosine. You can't mix thymine with a cytosine. It doesn't work. You can only mix these 2 base pairs together. Okay? Okay. Anyway, this is not a biochem class, so we're going to kind of go over this or skip past this. My thing doesn't work. There we go. So we've seen this picture before, and we saw it when it came to surface tension to explain, how surface tension works. But we're also going to use this picture to talk about something called vapor pressure. And maybe you've heard that term before, maybe not, but this is related to how things evaporate. So how do liquids turn into gas without being boiled? So what you have to realize is that the surface molecules are less tightly bound to the liquid than the interior molecules. One, for the same reason, we don't have an extra molecule on top that's creating the opposite, that's creating another pull, so there's a place for it to escape on top. These molecules, let's put it this way, they just are not as tightly held as interior molecules. Okay. And so what will happen is you'll get random amounts of energy. Just these molecules are bouncing against each other. They transfer kinetic energy randomly. So think pool, billiards, when you hit the ball. When you break the what is it called? When you start and you break the little diamond thing, the triangle thing, all the balls. They go flying. All the balls have different speeds. Some are going fast, some are going slow. When one fast ball hits one that's stopped, the stopped one will start, and the fast one is going to be stopped. So all these different transfers of kinetic energy happen. That's the same thing that happens with molecules in a liquid. And sometimes a molecule on the surface will receive a large enough amount of kinetic energy that will give it the right amount of energy to break the intermolecular forces that are holding it to it near its neighbors. And when that happens, this thing will turn into a gas, and then it just goes flying. If the container's open, it'll just keep going. And that's what happens with evaporation. So let's kind of look at that in detail. So if the kinetic energy is large enough to break free from the IMFs from its neighbors, it will turn into a gas. So we're going to start off with talking about this thing called kinetic molecular theory. And this is just kind of an idea of just kind of how do you think about a large number of molecules and how they're moving, and how do you describe it? How do you track their energies and stuff like that? So the idea is the temperature of a substance is directly proportional to the kinetic energy. The average kinetic energy of your molecules. Right? Every individual molecule in your liquid is going to have a different kinetic energy. Some are going fast, some are going slow, so some will have large amounts of kinetic energy, some will have small amounts. But the average kinetic energy of all of the particles will be proportional to the temperature. And in physics, the kinetic energy, just don't forget, is proportional to the mass times the velocity squared. Okay, so the more kinetic energy they have, the faster they're going to go. Yes?
So this like when running things together like creates like fire sometimes?
So that is more, you're using the concept of friction to generate energy. And so, so that is also, you're causing molecules to have a large amount of kinetic energy when you do that. And sometimes it'll be so much kinetic energy it'll combust, it'll start burning. But this is I don't know. I'm not. It's similar, but here we're just thinking about what does temperature do. All right. So if you have a cold substance, some things can still be moving fast, but on average, your kinetic energies of all your molecules are low. When something's hot, your average kinetic energies are high. All right, so here are some molecules moving slowly at a low temperature. Here are some molecules moving very quickly at a high temperature. And the drawing is kind of showing you that some are going very fast, some are going slower. The trail, I guess, is an indication of how fast they're going. But you get a variation, okay? And we've seen this curve before, but we're going to kind of talk about it in more detail now. This is called a Boltzmann distribution, and this is kind of a representation of the kinetic energies of all the molecules. So focus on one curve first, like this T1 curve. On the y-axis, we have kinetic energy. So here you've got 0 up to a really large amount of kinetic energy. So you can kind of, don't do this, it's not exact, but you can kind of think of this as speed. So this is going slow, these are going faster. And this is, on the y-axis, the number of particles. And so the larger the curve, then the more particles are moving at that speed. So all this is saying is you've got a very small number of particles that are going really slow. You've got a really large number of particles that are going this kinetic energy, this speed. And then as you go to higher and higher kinetic energies, there's fewer and fewer molecules with those kinetic energies. But this is not a symmetric curve. It's not parabolic. It kind of shoots up, and then it just tapers off very slowly. Now, what happens is when you increase the temperature, the most probable kinetic energy shifts to the right. So now the new most probable kinetic energy is going to be further to the right. All right, the higher your temperature, the higher your average kinetic energy. Most probable and average are not the same. We'll talk about that in a second. The other thing that happens is this curve broadens out. So instead of being more narrow, you've got a smaller distribution of energies. You've got a bigger distribution of energies at higher temperature. So it's kind of more random. So which one of these is the most probable? If I asked you which point on that curve represents the most probable kinetic energy, what would you say? select. So the idea is I pick a molecule at random. What kinetic energy am I most likely going to pick? Okay. So, guys, excellent. The answer is B. If I am going to pick any random molecule, most of them are at this energy. That's why it's the tallest point in the curve. So most likely, I'm going to pick one of those. I mean, this is probability. It doesn't guarantee I'm going to pick that, but the most likely molecule I'm going to pick is going to have that kinetic energy, where the tallest part of that graph is. However, what is the average kinetic energy? Now let me turn that off again. Oh my God, this thing. I could change batteries. What is the average kinetic energy of all of my molecules? So, average, excellent. I think we talked about this already. So, it is C. And the reason C is the average is because of the shape of the curve. It's not completely parabolic. It's not a perfect U. If it was a perfect U, the average would be right in the middle. But since it tapers off in this direction, the average is kind of just to the right of that peak. All right? So it's somewhere here. You don't have to know exactly where it is. Just know it's somewhere there. Okay? There we go. Okay. So, when we say that the temperature is proportional to the kinetic energy, if this is measured at one temperature, and I increase the temperature, well, remember what happens? The peak shifts over, and then the curve broadens out. Well, the average is going to increase. And that's kind of what happens here. The average kinetic energy is increased as I increase the temperature. Now, let's talk about what this curve means when it comes to evaporation. Which shaded region above would represent a fraction of molecules with enough kinetic energy to escape the surface of a liquid? This is similar to something we've seen already. And you don't need to have taken calculus, but if you have taken calculus, hopefully this makes a lot more sense now. Area under the curve. It's an integration, right? So, if we're talking about escaping the surface of a liquid, we need a lot of energy to do that. We need enough energy to break with the intermolecular forces that are keeping that molecule in the liquid. So you need a lot of energy. You need to have on this high side. So it needs to be over here. The higher, the better. So the green side here, which is what most of you are voting for, the green side here represents high amounts of energy. So any molecule that has a large amount of kinetic energy will have enough energy to break with their neighbors, to break the intermolecular forces with their neighbors, and leave. This up here, just because it's high on the curve, doesn't mean it has enough energy, right? The energy here is kind of in the middle. This might not be enough energy. We don't know exactly where the threshold is, but this might not be enough energy to break with their neighbors. So we want the most energy possible, and anything up here is going to work. Where this stops is kind of variable. It depends on what kind of stuff we're talking about. Yeah?
Sometimes I'm kind of confused. What does number of particles mean, like in this case?
So, think if you have a vial of some liquid, water, and there's 10 to the 23 molecules, right? So those 10 to the 23 molecules are all represented in this graph. So the idea here is, I don't know if you've taken calculus, have you? Okay, so let me think. So if I break this up into slices, right? Slice, 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 and every slice represents a a group of molecules that have that particular energy. If I add up all of those slices, so whatever the number of particles here, the number of particles here, number of particles here, that should add up to all of the molecules in my container. So these number of particles could be, you know, a large number. But like here, this, you know, whatever this kinetic energy is, wherever I am on the x-axis, what I'm saying is I've got a large number of my molecules. Think of this as fraction, actually. So think of, God, it'd be better if you had calculus, but think of it as a fraction. So 100% is way up the top. We can't see it. And maybe this is like 1% of molecules.
Oh,
This
yeah,
is 2%. That's 3%.
Yeah.
And if you add up all the slices, you'll get to 100%.
That makes more sense.
There we go. There you go. That's a good one. So in calculus, by the way, just in case, if you would integrate, the area under the curve represents all the molecules.
Okay, yeah.
Okay. So yeah, there's a lot of molecules that have this mid-level energy, but that might not be enough energy to escape. So you need lots of energy to escape, and only a small fraction have it. Okay? Which is why evaporation is so slow. All right? Only a few molecules have the right amount of energy to escape. And what's the other condition? They have to not just have the right energy, they have to be at the surface. If they're not at the surface, by the time they get to the surface, they might have lost their energy. They'd collide with other molecules and stuff. So there's a lot of things going on. So let's talk about something called evaporative cooling. So sweating takes advantage of this concept called evaporative cooling. If I take some of my molecules that have a lot of energy and they evaporate, they leave, they turn into a gas, what happens to the overall energy that's left behind? Is it higher or lower?
Lower.
It's lower, right? Some of my highest energy molecules have left, and now the average kinetic energy, it's going to be lower. And since average kinetic energy is proportional to the temperature should be lower. That's exactly what happens when you sweat. All right? When you sweat, your body releases liquid. It expects to evaporate. Your body wants it to evaporate, and when it does, it takes that energy with it. When your sweat evaporates, turns into a gas, turns into vapor, it takes that energy that it used to evaporate with it, and now your overall kinetic energy is lower, and so your body temperature will be lower. It cools you. We're actually going to do an experiment like this in lab probably next week, where we'll look at different liquids, and we'll see how much evaporative cooling we can do based on when they evaporate. If anybody's ever done anything with acetone, if you've had it evaporate off your fingers, it feels really cold when it does that. And that's because when it turns into a gas, it takes that energy with it that it used to turn into a gas. And your overall average kinetic energy that's left behind is lower because the high energy molecule left. And that means your temperature has gone down. So I won't turn this on, but the remaining temperature of the remaining liquid would be less once something happens. That's what evaporative cooling is. Okay, so this is a little bit complicated. I'll give you the time to wrap your head around it. If I were to tell you that I have two substances, substance A and substance B, and substance A had stronger intermolecular forces than substance B, then what would your Boltzmann distribution look like? So if you had two substances, they're both at the same temperature. So if they're both at the same temperature, they'll have identical Boltzmann distributions. But one of these has a threshold where it turns into a gas at a different spot than the other one does. So which one of these graphs makes sense, graph A or graph B, if substance A has stronger intermolecular forces? So again, these lines, whether it's this way or this way, these lines represent the energy threshold that they need in order to turn into a gas.
Wait, did you just say that it doesn't matter, like, if it's B or A first?
Well, it does. So one of them is correct. So it's either B or A first. A first, or is it B first?
I don't.
And so what I'm telling you is that the
okay.
intermolecular forces for A are stronger.
Oh, okay.
This is a kind of a test to make sure that you understand a little bit of what this Boltzmann distribution is telling you. All right, so let's see. Not bad, not bad. It is B.
Pretty easy question.
It is confusing, I agree. But it's kind of one of those you have to kind of think, well, what is this telling you? So first, whether they're two different substances or not, as long as they're at the same temperature, the Boltzmann distribution looks exactly the same. And that's because what does a Boltzmann distribution do? It tells you the distribution of kinetic energies. So if they have the same temperature, they're going to have the same distribution of kinetic energies. Yeah.
So I'm just confused because it wouldn't, if A has bigger intermolecular forces, which means they're like not as easily able to break apart, right?
Right.
Wouldn't it have less energy, so A would be first?
Well, so if they have stronger IMFs, then it needs more. You need more energy to break them apart.
Right.
And so, what this is saying, oh, all of these molecules past this line have enough energy to escape, and for B, only these have enough energy to escape. So this is actually backwards, because if A has stronger IMFs, I would expect it's easier to vaporize B. Right? So if B is easier to vaporize, then the threshold, the energy threshold, so the minimum energy you need to vaporize should be lower. So B is going to have require less energy to vaporize your liquid. Okay. Okay. So, given that information, which one of these substances, A or B, would cool down more, would cause the biggest drop in temperature? So if I take two of the same things, I let them both evaporate, which one would cause a bigger drop in temperature?
Is it relative to how many there are then also?
Mhm.
Okay.
Yes. So think about, yeah. When evaporation happens, the liquids, molecules that had the right temperature, that had the right kinetic energy, are now going to turn into a gas. They're going to leave. And then think about, well, what happens to the remaining liquid? What happens to the average kinetic energy? And then thus, what happens to the temperature? So, everybody got it right? Who voted? So here, if it only takes this much energy to vaporize B, then all of these molecules can evaporate. That's a lot more than A does. A only has a smaller amount, but all of these can evaporate. And if all of these evaporate, now the average kinetic energy is going to be dropped down because I've taken away some high energy molecules. My average is going to drop. And if the average kinetic energy drops, the temperature will drop.
Wait, do we decide that B evaporates less?
B evaporates more.
Evaporates more, but I thought.
Because the intermolecular forces of B are weaker,
Oh right, okay, so
so it's easier to break the connections between
Right,
B
okay.
molecules, right? And so if B evaporates more at the same temperature, at the same conditions, it'll cool more.
Right.
More molecules will be lost. The average kinetic energy overall is going to drop. So after you take these out, you'll redo the whole distribution, and the curve will now be shifted over to the left. The average kinetic energy will be shifted to the left. The temperature will be dropped. Okay? If you need a real model to think of acetone versus water. All right? Water has stronger IMFs. Acetone is weaker. Not as weak, but it's weaker. not super weak, I should say, but it is weaker. If I let water evaporate, yeah, I can feel the cooling a little bit, but if I let acetone evaporate off my fingers, it gets cold a lot faster. And that's because acetone has weaker IMFs. So more of the molecules will evaporate faster. It'll drop the temperature faster. Okay. So now let's talk about how temperature affects evaporation. So we kind of looked at how IMFs affect evaporation, right? So different IMFs will change that threshold, where that minimum energy is. Well, what about temperature? What does temperature do? So if I take 20-degree water versus 50-degree water, which one evaporates faster? Hopefully you'd answer, well, 50-degree water will evaporate faster. Why is that? So temperature 1, this is the blue curve here. Let's just say I'll make up some numbers. Let's say that's 20-degree water. So 20 degrees C, that's room temperature, or slightly cooler. The most probable energy is here. All right. So now we're not doing energy on this x-axis, we're doing speed. So remember that kinetic energy is equal to 1/2 mass times the velocity squared, or speed. So they're somewhat proportional. One is squared, but it's a similar idea, okay? And so the average is somewhere here, just a little bit past the curve. You still get these Boltzmann distributions where it tapers off a little bit on the right side. But that threshold is not going to change. So for any substance you're looking at, there is a minimum energy for them to turn into a liquid, or to a gas. Right? There's a minimum energy needed to break your IMFs. That's not going to change. So if I were to increase the temperature of my liquid, what does temperature do? Well, the temperature is going to shift that peak over to the right. It's going to broaden this distribution out. And now, this minimum threshold, there are a lot more molecules underneath this curve, underneath this red curve, than there are under the blue curve. So at a higher temperature, there are many, many more molecules that have that minimum energy to turn into a gas now. And so the higher your temperature, the more molecules you'll have that have that energy. So molecules will evaporate a lot more quickly at a higher temperature. And I think you can kind of visualize it as well. So the higher the temperature, the higher the average kinetic energy. Molecules are moving faster on average. They'll have more likely more energy, the right amount of energy to break those IMFs. All right, same curve, same idea. Here we're explicitly showing this dotted line. That's the minimum energy we need in this particular case to turn into a gas. And at a higher temperature, the area under this curve is a lot bigger than the blue curve. And so there are more molecules. The area under the curve is proportional to the number of molecules that have that right energy. So let's kind of change the scenario a little bit just so we understand. If I were to take any liquid and leave it in a container that's open over a large amount of time, that some of those molecules will turn into a gas, and if the container's open, those gas molecules will leave forever. They won't come back. And the remaining molecules are going to redistribute their kinetic energy. They're going to absorb more energy from the surroundings. They'll remake that Boltzmann distribution just like before, and there'll be enough molecules. There'll be more molecules with the right amount of energy to leave again. So over a long period of time, all these molecules will disappear. They'll all evaporate. We've seen that in real life. Everybody has seen water evaporate. Okay. Well, what if we cover it? Okay. So we cover it, we seal it. Well, evaporation still happens. So there are liquid molecules, even in a closed container, that are turning into gas. But now that they're in a sealed container, well, what will happen? These gas particles will bounce around and eventually hit the surface of the liquid again. At which point, they can bounce back out, or they can get reabsorbed and turned back into a liquid. So when those gas particles hit the liquid surface again, they can lose some of their kinetic energy by colliding with the neighbors. And maybe they'll lose enough energy to now be stuck. The IMFs take over and they're now back to a liquid. But at the same time as some of these gas particles turn back into a liquid, there's going to be other liquid particles turning into gas. And so there's this constant back and forth. There's going to be liquid particles turning into gas particles turning back into a liquid. We call this an equilibrium. And in this case, it looks like the amounts of gas particles and the amount of liquid particles don't change. So at some point, there's going to be an equilibrium where, I'm going to have a certain amount of liquid, I'm going to have a certain amount of gas. It's going to be a fixed amount. It's not going to be static, meaning, certain gas particles will turn back into liquid, certain liquid particles will turn into a gas. It's what we call a dynamic equilibrium, where it looks like the amounts aren't changing. They are changing, but the actual numbers are staying the same. Okay, that's what we call an equilibrium. And we can actually measure the amount of gas particles that are in there. And we call that the vapor pressure. Okay, so vapor pressure. So, what is a vapor pressure? So first, let's talk about pressure in very broad ideas. So a pressure is how we measure gas. There's many ways to measure gas, but one of the ways we can measure a gas is by measuring its pressure. A pressure is basically a force applied over an area, and we're going to get into that in a lot more detail later on when we talk about gases. But we measure the pressure using this thing called a manometer. This is an old school tool. And the more pressure there is, the more this level of mercury is going to get pushed downwards. So there's this opposing force. There's air pushing on this side, and there's the gas particles pushing on this side. So if the levels are uneven, that means there's a higher pressure inside here. Okay? And that's how we measure the pressure of a gas. That's, one of the old school ways to do it. So the higher the pressure, the more particles there are. Okay, that's pretty simple. And this is what happens with evaporation. So if I start with a liquid, I put it in a closed container, and I start measuring how much gas there is. How much, so I take a vacuum container with a vacuum in it, nothing in it, no air, nothing. I put a liquid in it, and then I measure the pressure inside. Well, what will happen is over time, the liquid will generate a gas. And so this is what this blue line is kind of showing you. This blue line is telling you how often the rate at which liquid particles turn into a gas. This is the rate of evaporation. And so it's constant. As soon as I put my liquid inside this container that has nothing else in it, some of that liquid will start turning into a gas. And the rate at which it turns into a gas is pretty constant. What's happening here is the opposite, liquid or gas turning back into a liquid. At first it's 0 because there was no gas. But as I slowly am creating more and more gas from this thing, the rate at which the gas turns back into a liquid starts going up. And in the point at which liquid turns into a gas and gas turns into a liquid, the rates are the same. The speed at which they do this are the same. That's what we call the equilibrium. All right, and that's when we say, okay, well, what's the pressure inside? That's the equilibrium vapor pressure. So just kind of an idea how we measure it. This is overly complicated. It's not that hard. So here's a kind of a picture of what I was just talking about. You start with a container with nothing, no gas, put a liquid in it. Immediately that liquid will start generating some gas. Some evaporation happens. But as soon as I start making gas, some of that gas will go back into a liquid. And at some point, you'll have equal amounts of gas turning into a liquid and liquid turning into gas. And at that point, when it's equal, the rates at which they go back and forth, that's what we call the equilibrium. All right. And you're going to learn all about equilibrium in 223. You'll have to do calculations based on equilibrium. It's not super. Actually, I like it, but some people don't like that. So here is how we measure vapor pressure. I mean, I showed you a slide before. This is a manometer. This manometer is a closed manometer. So on this side we have a vacuum, and so if I hook this up to a container that is also a vacuum, the two levels of mercury will be exactly the same. There's no pressure, so nothing pushing on this mercury to push this upwards. But as soon as I hook it up to a container that has any gas in it, which this thing will soon have some gas, the liquid's going to turn into gas particles. And now that I have a gas, these gas particles are going to push on the surface of the liquid mercury, and I can measure the pressure by measuring the difference in the height of these two mercury levels. All right, that's how we measure. I mean, that's the old school way to measure vapor pressure. We use more sophisticated pressure sensors now, because mercury is kind of dangerous. All right, so this is where it gets a little bit complicated as well. I have water and ethanol, okay? And if I put a drop of water on a surface versus a drop of ethanol on a surface, you'll see that ethanol will evaporate much more rapidly, okay? So if I have these two graphs that show temperature and vapor pressure, which one of these curves do you think belongs to ethanol? So think about what we're looking at here. So we've already seen how temperature affects vapor pressure. So as you increase the temperature of a substance, the amount of evaporation increases, right? So if the amount of evaporation increases, you should have a higher amount of gas, so higher vapor pressure. So which one of these will cause a faster increase in vapor pressure? Ethanol or water? Stop it in a minute. All right, if you're still struggling to understand what you're saying, that's okay. These are tough. So most people voted that A was ethanol. And so yeah, you'd be right. So how do you think about this? Well, just pick a temperature. Pick any temperature you want. Like, I don't know what this is, if it's room temperature or if it's warmer or something like that. Pick one temperature. And then if we, at that temperature, let's look at the vapor pressures of these two curves. So curve B has a low vapor pressure at this temperature. Curve A has a higher vapor pressure at this temperature. So what does that mean? A higher vapor pressure means it has more gas. So which one would you expect to have more gas at a certain temperature? Well, I would expect the one with the weaker IMFs, right? Something with a weaker intermolecular forces will allow more molecules to become a gas at a particular temperature. And so that's ethanol in this case. Ethanol has weaker IMFs than water does. They both do hydrogen bonding, but ethanol only does it with one side. Water does it in two sides. So ethanol should have more particles in the gas phase at a particular temperature. And that's why A is ethanol. Okay. So again, vapor pressure is just a measure of the number of particles, all right? Or it's not the measure of the number, but it's related to the number of particles in the gas phase. The higher the vapor pressure, the more particles you're going to have in the gas phase. Let's see if this demo works. I wasn't sure. Can be a commercial again. Yep. Oh yeah, these things. I remember now.
If you struggle to lose weight,
Alright.
you must see this.
Nope. Sorry.
A fat dissolving loophole has
Nope. BS. So look at this thing down here. The way these are constructed is you've got a bulb in the bottom with a bunch of liquid in it, and there is a glass straw that is not going all the way to the bottom, but pretty close. It's open, and that straw is connected to the top part. So when this thing was full, and you hold it in your hand, what's happening is the heat from your hand is causing more of the liquid particles to turn into a gas. So, yeah.
Just out of curiosity, I noticed kind of, well, let's say like you put your hand in the freezer so it's much at a much lower temperature, would it go up less, or would it still, the feeling, like just the, at least there's the feeling a little bit of heat around your hand?
I mean, your blood, you're not dead, so
Okay,
I think your hand would warm up pretty quickly. But yeah, then if your hand was super cold, then this wouldn't work as well. Yeah. But yeah, the heat from your hand is making the liquid hotter, and as the liquid gets hotter, it's making more vapor, right? The vapor pressure is going up, and so there's going to be more gas in this bulb down here because the liquid was way down here. It was full. Like in this case, you can't really see it very well, but it was full. So more gas is being generated right here. Well, where is that gas going to go if it's full of liquid? Well, the gas is going to push the liquid out of the way. The gas that's being formed is pushing the liquid up the straw. So there's no, I mean, this thing was full with liquid, so as you make more gas from the heat of your hand, that gas is pushing the liquid up the straw, and that's why all the liquid goes up there. It's a really weird phenomenon, but that's how it works. So that is a little different, and I don't know if we're going to get to it exactly, but in that case, the gas is dissolved in the liquid, and the higher your pressure, the more gas you can keep dissolved. So as soon as you release the pressure, some of that gas is going to undissolve, and that's why it bubbles a lot. But most of it stays dissolved until you heat it up or leave it forever, and then it'll come out. It's a slightly different phenomenon because we're talking about pure substances, and that's like a mixture, so more complicated, more complicated scenario. Okay, so these are the hand boilers. Come back to this. Here are these curves again, these vapor pressure curves that show as you increase the temperature, the vapor pressure of a liquid goes up. Now, again, we're going to talk about pressure in a lot more detail later on, but the units for pressure, there's a lot of different ones. One of the ones you'll see a lot is millimeters of mercury, which is a weird unit, but that literally comes from the tool, that manometer that I showed you. That's how the old school way to measure pressure. You measure the height of the mercury column, and they measure it in millimeters. So I think in the news you might see barometer readings, inches of mercury. Same thing. It's old school units, which we do use a lot still. So these are three different curves for water, for ethanol, and for ether, diethyl ether. And they should make sense if you pick a temperature, say room temperature, 20 degrees, 24 degrees, something like that. You can see that the vapor pressure for water is hardly anything. It's really low. So at really, really cool temperatures, you can leave a pool of water out, and it takes forever to evaporate, which is true. But something like ethanol has a higher vapor pressure at room temperature. And so over time, you'll see the alcohol evaporate pretty quickly. Diethyl ether, though, at about room temperature, I mean, the vapor pressure is huge. That stuff, if I leave it open, will fill up the room with gas pretty quickly, which is why we need to work with this like a fume hood, because otherwise we would kill ourselves with that, or set ourselves on fire and make an explosion because it's very flammable. Okay, so there's some other things we can do. So again, pressure. Let's talk about pressure again. Atmospheric pressure, the pressure that we exist under, is approximately 760 millimeters of mercury. There's a lot of ways to define that. 760 torr is another unit for pressure. Torr and millimeters of mercury are equivalent. Atmospheres is another unit of pressure that we use. But 1 atmosphere is the same as 760 millimeters of mercury. So that's the atmosphere that we exist under. If you're at sea level, its standard pressure is 760 millimeters of mercury. So notice that if you look at 700 millimeters of mercury on this graph, and you look at where water hits that line, it hits it at exactly 100 degrees C. So what this is showing you is that the vapor pressure and the boiling point are connected. So that boiling point that we, hey, when does the water start boiling? Goes from a liquid, turns into a gas. 100 degrees. Well, how is that related to vapor pressure? Which is the same phenomenon, liquid turned into a gas. Well, this is the point. So you can find the boiling point of any substance using a vapor pressure curve. Because what you look at is, well, when does the vapor pressure of the substance equal to the atmospheric pressure? And that's when the boiling point occurs. All right? So if I were to ask you, what's the boiling point of ethanol? You would look at this graph and you'd say, oh, at atmospheric pressure, 760 millimeters of mercury, the vapor pressure is, you get that vapor pressure at 78.5 degrees C. And then diethyl ether, it's the same at 34.6 degrees C. So again, at 78.5 degrees C, ethanol's vapor pressure will be 760 millimeters of mercury. It'll be the same as atmospheric pressure. And when the vapor pressure equals the atmospheric pressure, that's when something will boil. All right, so what else can we do with this? What if I'm living on a mountain and the atmospheric pressure on a mountain is lower? Right? The closer you are to space, the lower the pressure of your air is going to be. So high up in a mountain, you're going to be breathing lower pressure. So let's say the pressure up in the mountain is it's not going to be that low, but 600 millimeters of mercury. Well, what would you expect? Weird stuff would you expect? Well, if the pressure up in their mountain is 600 millimeters of mercury, well, the vapor pressure of water hits 600 at about 95 degrees C. So what's going to happen is, living on that mountain, your water is going to boil at 95 degrees C, not 100. All right? And so if you ever look at cooking instructions, if you were living in a high altitude area, they say cook longer. Well, why are you cooking longer? Well, anything you boil is going to reach 95 degrees C, which might not be hot enough to cook. If you're only cooking at 95 degrees C because you're boiling water, you need to cook longer. That's why high altitude instructions say to cook longer, because boiling points are lower at high altitude. All right, so we have that. All right, this is the same stuff. So what happens? So let's think about what physically happens. So when a liquid's vapor pressure reaches the atmospheric pressure, you get boiling. And, think about why that would happen. So the vapor pressure, right? This is defined as, you've got a liquid, this is sealed up, and you've got these gas particles from the liquid, right? Because that liquid has a certain vapor pressure. Well, if suddenly the vapor pressure is going to be equal to the atmospheric pressure, all right, let's think about it this way. So what is the definition of the vapor pressure? This is the pressure that has to exist for a liquid and a gas. I said this wrong. So a vapor pressure, if you've got a liquid that has a certain number, certain amount of intermolecular forces, those intermolecular forces are going to limit how much of that is going to turn to a gas. All right, but there's going to be some amount of gas that needs to exist, right? That equilibrium where the gas particles turn back into liquid, the liquid particles turn into a gas. A certain amount of this has to be in gas form. That's what the vapor pressure is. Well, let's say that we're at we have a liquid and its vapor pressure is now equal to the atmospheric pressure. Well, what's going to happen is this liquid needs to generate that particular pressure of gas, and it's never going to be able to generate exactly that pressure because the atmospheric pressure is already at that level or below it. And so what's going to happen is just all of this liquid is just going to turn into gas. It's just going to keep going. That's why boiling happens. So yeah, that's, maybe I didn't say it properly, perfectly, but that's why boiling happens. All right, so here's some numbers just to give you an idea. When you live in Denver, the pressure up in Denver, which is the Mile High City, is lower than normal atmospheric pressure. So if we live sea level, 1 atmosphere pressure, that's our normal pressure. We expect water to boil at 100 degrees C. In Denver, which has a lower atmospheric pressure, water boils at a lower temperature. If you're on Mount Whitney, the pressure is really low, and water boils at 87 degrees. If you're on Mount McKinley, I mean, the pressure is really low. I guess you need a ventilator at that point. And water boils at 83. And if you're at the highest peak, Mount Everest, you definitely need gas mask there. Water starts boiling at 78 degrees C. It's crazy. So let's. Any questions about vapor pressure? So.
I thought it did, but then I figured it's silly. So in a vacuum, there's no pressure. Obviously, there's no.
Yep. So there's no pressure in a vacuum. So what happens to liquids in a vacuum?
It's always gas.
They just turn to a gas. Yeah, because so at a certain temperature, that liquid will have a certain vapor pressure, and so the liquid will want to create that amount of gas. But if there's going to be a vacuum, it'll just keep making that gas. So yeah, most things will turn into a gas. Most liquids will turn into gas in a vacuum. Yeah.
Even us. Right?
Sorry?
Even us, right?
Yeah, well, our blood will boil, and it's exposed to vacuum. Space is not a perfect vacuum. Like it's not it is a vacuum. It's like bad, but it's not a perfect vacuum.
So it would turn to a gas, it turns to like ice or something?
It's a combination of things would happen. So when something boils, when something evaporates, what happens? It cools at the same time. And so at some point, our blood would freeze before it would completely turn to a gas. Because as the higher energy liquid is turning to a gas, that energy goes with it, and the rest of your blood is now going to be at a lower temperature, and it will just keep dropping in temperature until it freezes. But even solids, and we haven't talked about this, but even solids have a vapor pressure. We're not going to talk about it actually at all, but solids have a vapor pressure too, and eventually your ice blood will eventually evaporate as well. Yeah, it's weird. So we've been talking about liquids and gases. Let's kind of go over the whole concept of phase changes real quick. I think you guys mostly have learned this stuff, but we have formal names for all of these things. Liquid to solid, solid to liquid, freezing and melting, that's pretty obvious. For liquid to gas, that's called vaporization. Gas to liquid, that's called condensation. I think those you've heard before as well. Solid to gas to solid, those might be newer, but solid to gas, that's called sublimation. Right? That's what dry ice does. When you leave dry ice out, it goes from a solid to a gas immediately. It doesn't go to liquid stage at all. And when a gas goes into a solid, that's deposition. Yeah.
This is like what was at the end of the homework that I was confused by.
Oh, okay. So maybe there was a little bit of new stuff in there. Sorry.
That's
okay.
Fine.
Okay. So deposition, and this happens in smaller dorm freezers and stuff. So your ice that you make in your ice trays in a little tiny freezer compartment will sublimate. The ice will eventually disappear, and they will deposit themselves on the surrounding little container, and you'll get all these frost crystals growing everywhere. So that's deposition. So let's talk about energy. And it's not as completely straightforward as you might think. So endothermic versus exothermic. First, the definitions. An endothermic process is something that absorbs energy, and an exothermic process is something that releases energy. So which ones are exothermic, which are endothermic? How much heat is required to release for those phase changes? This is something we're going to look at. So first, enthalpy. We're going to define this, and it's not going to be a very satisfying explanation. So enthalpy is defined as the heat content of a substance at constant pressure. And there are more technical definitions of what enthalpy is. If you want, I can show it to you, and then you'll be like, I have no idea what that means, which is fine. So enthalpy is defined as internal energy plus pressure times volume. And so again, like, I don't know what that means. You don't have to know that. That's okay. That's the more technical definition of what enthalpy is. So that is kind of a description of what it really means. Ultimately, we're going to be using enthalpy a lot. And the reason we like to use enthalpy in chemistry is when it creates a lot of simplifications for us. Let's put it this way. A lot of the stuff that we're going to look at is done under constant pressure. So when I do an experiment in a lab, when I mix two chemicals together, I'm doing it under constant pressure. There's no change in the pressure, or the atmospheric pressure. Yes, I could be making bombs. I could be doing something in a sealed container. That's it. We don't really do that, though. So most of the things we're going to look at are going to be under constant pressure. And so when we make that condition for us, where everything's at constant pressure, the enthalpy, this concept of enthalpy, is a very convenient thermodynamic property to use to track energy changes. Okay, so that's what we're going to be interested in doing, is tracking energy changes. And enthalpy is going to be the easiest way for us to do that. So we're going to be looking at changes in enthalpy. And enthalpy is defined as H, right? And so change in enthalpy is going to be this delta H. So, again, don't worry about enthalpy overall. Just think of it as a way to track energy and at constant pressure. That's the condition. Well, there doesn't have to be at constant pressure, but it gets more complicated that way. So here are all the phase changes. And what you can see here is the lowest enthalpy state possible is when you have a solid. That should make sense. If a molecule is in a solid form, it's not moving very much. Not much kinetic energy going on. If I want to turn it into a liquid, I have to give it energy. I have to melt it. All right, I have to start letting those molecules move around in the liquid state. All right, they're not stuck in a crystal anymore. So that requires a little bit of energy. But if I want to take that liquid and vaporize it, turn it into a gas, I have to give it a whole lot more energy because those gas particles are moving faster. So these are endothermic changes. Right? The system itself is absorbing the energy. I have to give my water some energy to melt it. I have to give ice. I have to give the ice some energy to melt it. I have to give the water some energy to turn it into a gas. So those are all endothermic. And notice that the sublimation change is exactly the same as the melting plus the vaporization added together. So going from a solid directly to a gas is the same energy change as doing it step by step. Solid to liquid, then liquid to gas. Yeah?
Which one's absorbing energy again?
Endothermic. Endo. So on the opposite side, we have exothermic process, and the energy changes are exactly the same. They're just in the opposite direction. So an endothermic process, on the left side, these red ones, these are all positive changes in energy, right? The substance itself is absorbing the energy. The energy is going up. These are positive changes. Whereas on the right side, we have negative changes in energy. Actually, ignore this sign for a second. Negative changes. The enthalpy of vaporization, right? That is literally the amount of energy I need to vaporize something is exactly the opposite energy I need to turn something from a gas back to a liquid, to condense it. All right, so these are fixed energies, right? So if I vaporize something, I have to add a certain amount of energy. To condense it, I have to take away the exact same amount of energy. So freezing is the opposite of melting. Deposition is the opposite of sublimation. Now, I want to address this little group of letters, FUS. So all the rest of them hopefully make sense. Sublimation, vaporization. Why doesn't this say melt or something like that? So the melting one has a weird name. It's called the enthalpy of fusion. And it sounds the opposite of what it is, but that's what it is. So when you see enthalpy of fusion, this is the energy required for melting. So it sounds like the opposite of what it really is, but that's what it is. Enthalpy of fusion is what you need to melt something, right? Okay. I do not know the origin of that term either, honestly. We just learned it. Okay. Going from a liquid to a gas or gas to a liquid. For liquid to a gas, you'll need the enthalpy of vaporization. If you want to go the opposite way, it's the enthalpy of condensation. These two numbers are exactly the same, just opposite sign. All right, so the heat of vaporization is a positive enthalpy change. The heat of condensation is a negative enthalpy change. By the way, I keep saying heat versus enthalpy. I keep interchanging them. And that's another thing that happens a lot in chemistry. These two words kind of are interchangeable. So if you see the word heat of vaporization, that's the same thing as enthalpy of vaporization. Okay. So it should kind of make sense why these are positive. These require energy. Because to vaporize something, you need to break the IMFs, and that requires energy. When you're forming the liquid again, gas back to liquid, you are getting those IMF interactions back. And so you release energy when that happens. Okay? Okay. Yeah, so these opposites, these are always true. So heat of fusion versus heat of crystallization. That's another one that's a little bit different. So we have melting and we have freezing. But we don't call it heat of freezing or enthalpy of freezing. We call it enthalpy of crystallization. We don't call it enthalpy of fusion or melting. We call it enthalpy of fusion.
Can you go back? I didn't get the
Yep.
condensation one really.
Yeah.
I got it.
Okay. So a lot of terms here we're throwing out, but most of them kind of work. This is the one where it's a little bit weird. So melting, heat of fusion. Freezing, heat of crystallization, or enthalpy of crystallization. And again, one's positive, one's negative, but they're exactly the same number. They're just opposite signs. So let's get to, oh my God, where is this? Moog page 94. Let's find what it is. This is, I guess it's 25C, which, or is it 25C? It is 20, no, it is not even anything. Hopefully this is in your manuals. So, I didn't get a chance to look and see. It comes right after 25B, so somewhere around page 90 something. There should be a section that starts with liquids and enthalpy of vaporization. You guys see it? Is it in yours?
Is 88.
88. All right, thank you.
90 is C profit.
All right, so let's take a look at these numbers 1 through 8, and let's make sure that these make sense to everybody. Okay. Page 88, you said? Yeah, 88. Yes. Yes.
How do I know which liquids require more or less energy, like based off?
So it's the same way. So it's the same way we looked at wave pressure. So it's all IMFs. So the stronger the IMFs, the more energy you're going to need to get in. Okay.
And hydrogen bonds have.
So molecules that can do hydrogen bonding are going to have the strongest IMFs. Then you look at dipole-dipole interactions, and then beyond that, you look at dispersion forces. Just right, yeah.
Wait, oh.
Yeah.
Is this our first one, or is this the one from last week?
This is a while. This is from week 2.
So our first lab.
Yeah.
Okay,
the
that-
first one that you needed. to do
Yeah, I was
that
about
for.
to say, like, I thought I did my full chart for last week.
Yeah, it's not here.
Oh yeah. This, I think I both like typed in the entire thing and tried to copy the link. There was like nothing came up.
I think there was like an L versus a 1 maybe issue, but it's okay.
Oh, okay.
A lot of people had issues. We need to come up with a better system than that. It's all right. Okay, caught up. All right, how's it going? We need to go over some stuff.
Yeah.
All right. So we've got these three liquids, which requires the least energy per mole to vaporize. So this is all IMFs, right? So we need to break the intermolecular forces in order to make them turn into a gas. So the one that has the strongest IMFs, that's going to be water. Water has two sides that does hydrogen bonding. That's better than methanol, which only has one side, which is better than hexanes, which is nonpolar. Which has the least energy per mole to vaporize. That's hexane, the least. The most would be water, excuse me. So hexane doesn't take much energy at all to break the forces that hold them together. I think the boiling point for hexane is going to be like 60 degrees C or something like that, maybe less. It's pretty low. Is the delta H, the heat enthalpy of vaporization for these liquids, positive or negative? So any vaporization energy change is going to be positive. You have to add energy to anything to cause it to turn into a gas, to vaporize it. So they're all going to be different values, but they're all going to be positive. For which liquid is the absolute value of delta H the smallest? Which one? Yeah, hexane is going to have the smallest value, and they say absolute value so that you don't know it's positive or negative. So whether it's negative or positive, hexane, it's going to be positive. Hexane is going to have the smallest value. And then the largest is going to be water. So 5, and this is kind of something we're going to have to start doing mentally for a lot of things, is sketching an energy change for delta H for each liquid evaporating. So the idea here is if I have an energy diagram, or in this case enthalpy diagram, just think of enthalpy and energy as interchangeable somewhat. And I start all my liquids at whatever this energy is. Well, to go from here to gas won't require a big jump for hexane. So only a small jump is required. You only have to add a little bit of energy. But for methanol, it would be up here, and water up here. Methanol. So methanol would require a lot of energy. Water would require the greatest amount of energy to turn into a gas. Okay? So that's what we're measuring here is the change in enthalpy. There's a delta H here, a delta H here, and a delta H for this one. And so the delta H for enthalpy, for hexane is going to be small. The delta H for methanol is going to be larger. The delta H for water is going to be the largest. Okay? So 6, sketch a Maxwell-Boltzmann distribution, or just Boltzmann distribution, for each substance. They are all initially at the same temperature. Assume the each sample contains the same number of moles. All right, I tried to emphasize this, but if you have a distribution, a Boltzmann distribution, and you've got kinetic energy on your x-axis, then if they're at the same temperature, well, kinetic energy is proportional to temperature, and that's it, nothing else. There's nothing in here that says anything about the IMFs. There's nothing in here that says anything about the molar weights. Nothing. It's just proportional to temperature. So if they're all the same temperature, then they'll all have the same average kinetic energy. I forgot to put average in there. So they'll have the same Boltzmann distribution if they're at the same temperature. And so the generic Boltzmann distribution looks like this. It goes up, and then it just kind of tapers off like that. They'll all have the same one, exactly the same, if they're the same temperature. All right, that's if there's kinetic energy here. If it's velocity, then we're talking different. Because then, what is kinetic energy's equation in terms of velocity? Kinetic energy is 1/2 mv squared. So now, if I look at, well, how does velocity change with temperature? There's masses involved there too. So the mass is going to play a role. It's going to be more complicated. But if it's just the average kinetic energy, if this kinetic energy is on the x-axis here, they're all the same. It's one temperature, so they all look the same. We're gonna look at velocity in a little bit too. Don't worry. So the label, the relative kinetic energy of vaporization for each substance on the curve. So what they're saying is there is a threshold where these molecules were turned into a gas, right? That's the idea. So where is that? What's that minimum energy required for these liquid molecules to turn into a gas? Well, for hexanes, it's going to be way down here. All right, so I'm going to label this one as hexane. So there's going to be a large number of molecules past this threshold that are ready to turn into a gas. For methanol, it'll be higher because you're going to have to break more IMFs. And for water, it's going to be even higher. So only a small number of molecules, anything past this line, is going to be ready to vaporize. You know, the spacing, you know, where exactly they are, that's variable. I don't know exactly, but this is where they relative are going to be. Hexanes first, methanol, then water. All right, because this has the weakest IMFs, this has the strongest IMFs. So now, why does the delta H of vaporization, why is it so much larger than the delta H of fusion? And we have a little graph down here that kind of shows delta H of fusion here, delta H of vaporization, delta H of fusion, delta H of vaporization. Why is delta H of vaporization so much bigger? So what is delta H of fusion? What is that describing? Melting, solid to liquid. And then vaporization is liquid to gas. So why is liquid to gas require so much more energy than solid to liquid?
Because you're dealing with more kinetic, actually, I don't know, but
There's a stronger IMF for, like, the bonds are tighter within solids than in liquids.
Well, think of the positions of the molecules. When you go from solid to liquid, are you completely breaking the IMFs? They're still close together, right? So you're not, when you're melting, you're not completely breaking the intermolecular forces. You're weakening them so that they're no longer rigid in a solid. But the IMFs are still there holding the molecules together. Liquid to gas, though, you are completely breaking the IMFs. And that's why the liquid to gas change requires so much more energy, because you're completely breaking those intermolecular forces. Whereas solid to liquid, you're just weakening the IMFs. You're allowing the molecules to now slide around each other. But they're still attracted to each other. They're still feeling each other's partial charges. So you're not completely breaking the IMFs when you're melting. But when you're vaporizing, you're completely breaking the IMFs. And that's why it's a much larger energy change required. More energy is required to do that. Okay. I mean, it's pretty across the board. Some variations here and there, but it's pretty much that's the trend. Okay. So, this was just to kind of get a handle on what these numbers look like, how they might change based on IMFs. Let's get back to this. So now we're getting to the bane of people's existence in 222, Chem 222, and that is the Clausius-Clapeyron equation. And this looks like a nightmare, but we'll get through it, okay? So what this is doing is this equation is how you can basically plot these vapor pressure curves. All right, so this EXP, by the way, is the types notation for the E symbol. And I don't mean the E that does the times 10 to the power thing. I mean it's the Euler's E, the reverse of a natural log, right? That E.
2.7?
Yeah, 2.3, or is it 2.7?
I don't know.
Okay, I can't remember the exact number, but it's that E, okay? So that's what this EXP is. That's the E value, the Euler's number. So let's kind of break this apart. This equation lets you calculate a vapor pressure of any gas, assuming you know the delta H of vaporization and a specific temperature. R is a constant. This is called the gas constant. We're going to see this a lot. And beta is another constant. And this is actually not going to be that important, and I'll show you why. Because we're hardly ever going to use this equation in this form. But this is an exponential equation. That's why you get these exponential curves. This is the form of the equation we're most likely going to see. And the way you go from this to this is by taking the natural log of both sides. So let me do that just so that we have it, so that you've seen it done. You don't have to do this yourself, don't worry. But I'll show you the algebra just in case. When I take this equation, I'm just going to write P instead of P vaporization. Beta E to the power of minus delta H vape over RT. So I'm going to take the natural log of both sides. So take the natural log of this times the natural log of this. And the way a natural log works is anything that is multiplied inside of the natural log, or any log, you can separate it as natural log of beta plus natural log of E to the minus delta H vape over RT. That's how logs work. I'm going to stop using red. And natural log of anything to the E, this exponent comes out. That's how algebraically, that's how this works. So this exponent, natural log of the E, this exponent comes out, and the natural log of E is 1. So basically you end up with natural log of P is equal to natural log beta plus, actually not plus because there's the minus there, minus delta H vaporization over RT. Now, we're going to modify this even further because what we want to do is turn this equation into a form that mimics a straight line. And the generic equation for any line in algebra is y is equal to mx plus b. M is your slope, b is your y-intercept. So if I rearrange this equation, if I put the delta H over R, this is a constant for a specific substance, that's a constant for the gas constant. This is your variable. So I'm going to put delta H vape together and R together, and I'm going to keep 1 over T separate. And what I'm going to do is my 1 over t is going to be my x value. My natural log of b, beta, is going to be my y-intercept. My slope is going to be negative delta H vapor over R. And my y is going to be natural log of p. So this is a better, more useful form of the Clausius-Clapeyron equation. And the reason for that is because now I can measure, I can take any substance, ethanol, and I can measure its temperature, or let's put it this way. I can set it at a certain temperature, and I can measure its vapor pressure and get a data point. And then I can do a new temperature and measure a new vapor pressure, and then get a new temperature and get a new vapor pressure. And I can plot this as, on the x-axis, 1 over temperature. On the y-axis, I'll plot natural log of the vapor pressure. And my slope will have this in it, which is a way how I can measure delta H of vaporization. This is basically a way to calculate an enthalpy of vaporization for any substance. So this is the kind of graph you might get from that kind of data. So basically here I've measured a series of vapor pressures at different temperatures. And instead of plotting the pressure versus the temperature directly, I'm plotting the inverse temperature, 1 over T, versus the natural log of the vapor pressure. And I get this. So just really quickly, which way is temperature going? Or which way is temperature increasing? Yeah. Yeah. It's okay. So it's going to the left. Yes, everybody got it. So temperature increases going this way because it's 1 over temperature, right? So if I go 1 over 10, it's a tenth. If I go 1 over 20, that's a smaller value, right? So it's going to the left as you're increasing. So what does this fit tell us? Well, when I plot my inverse temperature versus natural log of the vapor pressure, so I've measured a whole bunch of vapor pressures at different temperatures. I've transformed my data to fit this graph, and I've plotted a straight line fit. The equation of this line is this. Well, what does this tell us? Well, I'm going to look at the slope. That slope, minus 2,993.8, that slope is equal to this whole thing, delta H vaporization over R negative. So I can take that number. So there's the equation rewritten properly. I can take that number and I can solve for the delta H of vaporization. So here's R. This is the gas constant. It's 8.314 joules per mole per Kelvin. If you go look on the gas constant on Google or whatever search engine you use, you're going to find a lot of different values of R. They're all correct. They all have different units, though. So pay attention to the units you're going to use for the particular value of R you're using. This is the one we want for this equation because it has joules in it. So once I know what R is, my slope, again, right here, this whole term is your slope. My slope is equal to negative delta H vaporization over R. So my slope for my graph is negative 2993.8. That goes there. I'm going to plug in the gas constant. Notice that it's already been transformed to kilojoules per mole instead of joules per mole. That's all that's happened here. And when you do the math and you solve for delta H of vaporization, you get 24.9 kilojoules per mole. Yes, question?
Is it really only that one and then, because I did this in my past one, and then this one is the only two we really ever use?
So yeah, we're going to use that one as well.
Yeah, are those like the only two that like really ever, or do you ever?
Yeah, that's the only ones we really use a lot. Yeah, but we're not going to get to that one yet. But yeah.
I just remember it.
Well, we have to do this on a test.
Yes.
It becomes really simple after a while, just 4 numbers after a while.
Yeah, yeah. Oh, the R? Yeah, yeah.
Oh, I'm just gonna.
Oh, this.
It's actually because this is the one thing I should remember doing.
Yeah, well, so this is, I mean, it looks like a nightmare, I agree. The Clausius-Clapeyron equation looks crazy. But once you get over how ugly it is, we're going to do the same thing every time. So once you've done it once, you've done it, and you know how to do it, okay? So We're going to try this on the board in a second, I believe. Or actually, we're about to go, aren't we? So the other thing you can get out of this is the beta constant. This is a less useful number for us because it doesn't really have much meaning to us. Delta H or vaporization definitely has meaning for us, so that's going to be a more useful thing. But if you ever needed to calculate beta, well, you get it from the y-intercept, right? So this whole thing is the y-intercept. There's my y-intercept in my equation, 18.01. So how do you do the inverse of a natural log? E to the power of whatever that is, right? So you take, that's it, that's the equation. 18.01 is equal to the natural log of b. To get rid of that natural log, you do e to the both sides. And again, this part comes right out. And you get e to the 18.01 is that number. All right. That's not as useful a number, but you'll get that in mastering chemistry. So let's try one of these on the board, and then we'll be done for today. But here is a set of data. Again, how did we get this data? Somebody went in the lab, took some mercury, set it at 25 degrees C or something like that, and measured the vapor pressure that it was generating. We have setups to do that. And then heated it up to 30 degrees, measure the vapor pressure. 35 degrees, measure the vapor pressure. 40 degrees, measure the vapor pressure. They have a series of temperature versus vapor pressure data. And then they plotted not the temperature and vapor pressure directly, but they plot the inverse temperature, 1 over T, and the natural log of the vapor pressure. And you get this nice straight line fit with this information. So there's your slope, there's your y-intercept. So what can we pull out of this? Well, again, according to the Clausius-Clapeyron equation, the slope, there it is, slope is equal to negative delta H vaporization over R. And so my slope is minus 7377. The units, we'll figure out the units in a little bit, okay? Negative delta H. And R is going to be, I'm going to use the original one that I showed you, that was on the slide, 8.31 joules per mole per Kelvin. So let's talk about units real quick before I do the math. Whenever you take the natural log of anything that has units, there is a math reason why this happens, but I'm not going to go into it. When you take the natural log of anything, the units disappear. So the natural log of vapor pressure has units, millimeters of mercury, atmospheres, whatever the pressure units are. When you take the log of it, or natural log of it, the units disappear. So this is unitless. So if the left side is unitless, all of these values have to become unitless when you put them together. So if this has to be inverse Kelvin, Kelvin is a unit of temperature, 1 over T is going to be 1 over Kelvin. This has to be Kelvin, then this has to be, 1 over Kelvin, this has to be Kelvin, so that when they multiply together, they cancel out. So basically, your slope value is going to have units of Kelvin. And if that explanation didn't make sense to you, it'll make sense when I do the math. So rearrange things. I'm going to put this up here. All right, so I'll end up with negative delta H vaporization is equal to, notice the Kelvin in the numerator and the Kelvin in the denominator. Those will cancel. And I'll be left with joules per mole. And minus 7377 times 8.31. Nope, 8.31, there we go. So I get negative 61303 joules per mole. Notice that both sides have a negative, so those go away, right? This becomes delta H vaporization is equal to positive 61303 joules per mole. And generally, delta H's enthalpies of anything are written in kilojoules per something, usually. This is fine, joules per mole, but if we want it in kilojoules, we'll divide by 1,000, and it becomes 61.3 kilojoules per mole. So that's how you calculate an enthalpy of vaporization from this kind of data. You're using the Clausius-Clapeyron equation to do that. And I think that's really the hardest thing about this, is just taking this graph and being able to come up with this number. That's it. All right, so you're using an ugly-looking equation and understanding that we're just using the linear form of it, this one right here, and understanding that we can get delta H out of the slope. We can do beta as well. I'll do that really quickly.
So you just did the delta H vaporization, right?
Yeah, I just did delta H of vaporization. That's it.
Okay.
So
And
you
the
get that from
equation
slope.
is the first one.
What's that?
The equation is the first one.
What do you mean the first one?
Like up there.
Oh, here?
Well,
Yeah. So this is the Clausius-Clapeyron equation. This equation is describing this line here.
Yeah. It says right the you know.
Right, the Clausius-Clapeyron for Hg. I think what is intended here is to take, you would basically do
is right
natural log of vapor pressure is equal to, you're basically replacing the slope
Right.
with like the actual numbers in there. So
Okay, yeah, okay.
negative 7.377 inverse Kelvin, all right, not inverse Kelvin, regular Kelvin, times 1 over T plus 18.47. That's what number 1 would be. Yeah.
Does this have anything to do with liter times ATM over Kelvin and then R?
So that's the other version of R, and you'll use that version of R when you're dealing with gas law equations. So if you need pressures and volumes, that's where you'll use that version of R, the Liter atmosphere one.
Okay, good to know. Okay.
Yeah. So if you're dealing with energy, you're going to use this version of R. So finally, if I ever wanted to get beta, the log of beta is our y-intercept, and it's 18.47. And to get rid of a log, you do e to the both sides. So e to the natural log of beta, e to the 18.47. The beta comes out, and you get normal beta is equal to this number. So on my calculator, my e value is right there. It's right on top of the natural log button. If you need help finding e on yours, here, let's see. The standard ones. So for these calculators, yeah, it's also right on top of the natural log. So second function, e to the x thing. So e to the 18.47 is some ridiculously large number, 1.05 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. And as far as I know, I think beta doesn't really have any units. I think. Or maybe it does. I can't remember. It's not something we care about too much, though. You'll do this in homework, but I don't care about beta. It's not a useful thing, so you won't really see it on the exams. But delta H is very important. Okay? So know how to do that. All right, that's it for today. We're out of time. We'll probably come back to this on Wednesday because we'll practice doing our own graphs. Did I get the right numbers? Yep. There it is. So we'll practice doing our own graphs. I think we'll do this in lab even. But we have a couple different forms of the Clausius-Clapeyron equation. Understand what they're used for, what they're good for. There's a third form that we'll see later. We'll do that on Wednesday. It might be helpful with homework. But we'll talk about that later. All right, see ya.
I'm just kind of curious. You know what? Do you know why? Like when I take a picture of this, it randomly just shows rainbowy. I don't know.
It's hard to say.
Weird. But it's only with this screen because I take pictures of the screen, but it's weirdly just this screen.
So it might be the sapphire lens and the way it diffracts light. I have no idea though.
Yeah, interesting.
I have no idea. That's optics. Oh, what happened? Oh well. All right. Questions for homework? Anything we can talk about? Anybody wants? So you mentioned gas dissolved in soda, and I kind of want to go over it, but it's not something we're actually going to go over. This is one of the sacrifices we make in this series of chems, is we don't really talk about what happens with mixtures, solutions, and like their boiling points and stuff. But carbon dioxide dissolved in water is interesting because normally, so like if you're trying to make more salt or more sugar dissolved in water, you would heat it up, right? You heat up water and you can get more salt to dissolve, or sugar to dissolve. But for gases, it's the opposite. You want it as cold as possible. And that's because the hotter you make it, the more energy the gas particles have and the more they can leave. Which is why hot soda loses its fizz really fast versus cold. But yeah, that's, we're not going to talk about it this time, but we can, feel free to read about it if you're curious about it.
Yeah, it just seems like 'cause as soon as you open the thing, then some of it's, and then there's gonna be a rated, which it's like leaving the liquid in the container.
Actually, you know what? Now that you're saying that, there's an equilibrium there as well. So as long as it's under high pressure, there's a lot of gas. That's what it means to be high pressure. A lot of gas in that little area on top of the bottle. Then you're basically forcing a lot of gas to be dissolved in water. But as soon as you let that pressure go, then less gas needs to be dissolved and it'll slowly lose its fizz. Right? So it has to stay at high pressure while it's being stored.
Yeah.
Yeah, equilibrium is a neat concept, and if you're going to take 223, that's